Hi, my name is Graham Bleaney. I'm a security engineer at Facebook. Today I'm going to be talking about how to apply Pysa to identify Python security vulnerabilities. We're going to start with an overview of Pysa and how we use it at Facebook. We'll go into the basic functionality, the concepts behind it, and how it's actually used. Then we'll discuss the implementation, how we actually build Pysa. After that, we'll talk about refining the signal and two of the tools that we offer to refine the signal that you get from Pysa, Sanitizers and Features. Then we'll move on to model generators, which cover how to generate models, a tool that Pysa needs for large code bases. And then finally, we'll discuss limitations and conclusions. So, I'm a security engineer at Facebook, and I'm an enthusiastic user of Pysa. Why should you trust me to talk about Pysa? Well, I've spent the last year and a half applying Pysa to Instagram and the other Python code bases at Facebook. Additionally, I've written most of the public documentation on Pysa. So what is Pysa? Pysa is a security-focused Python static analyzer built on top of Pyre. Pyre is Facebook's Python type checker. For those who aren't familiar with it, but are familiar with Python type checking, you might be familiar with MyPy, which is a similar tool. When I talk about static analysis throughout the presentation, the simplest way of thinking about it is just looking at code without running it. The goal of this presentation is for you to understand how Pysa works, and also to develop the confidence to apply Pysa to find vulnerabilities in Python code. By the end of this presentation, I want you to have the tools to tailor Pysa's output to be high signal on projects that are much larger than the sample projects we're going to be using today, up to millions of lines of code. So why did we build Pysa? At Facebook and throughout the security industry, there's this concept of shifting left, this idea that on this continuum of bug badness that you can see here, the best case scenario is preventing a bug, and the worst case scenario is having it be exploited. And as we move along this continuum, we're moving from best case to worst case. So after prevention, next best case scenario is automatically finding a bug. This is having the tooling to detect the bug without any human having to look at it. Next best case scenario is finding a bug manually. So having a security review or something that can catch a bug before it goes out to the world. After that, our next best case scenario is finding the bug externally. So Facebook has a bug bounty program, which we will pay external security researchers to report bugs to us. This isn't ideal because it means the bug's gotten out there, but at least we can find out about these bugs and get them fixed. As we move further to the right, we're getting into particularly bad scenarios. If a bug is never found and it continues to exist, that's not a good thing. And finally, if a bug is exploited, that's our absolute worst case scenario that we want to avoid. We built Pysa to be able to be on the leftmost portion of this continuum. So being a static analysis tool, it's obviously an automated tool that can find bugs automatically. However, if we can run Pysa when developers are proposing their changes and get them feedback and get that feedback fixed before their changes ever land, then we can even move into the prevention land on this continuum. So why did we build Pysa? Well, we knew from our work on Zonkalon that static analysis has a lot of potential. So when we previously talked publicly about Zonkalon, we said that it had found 1,100 issues of significant severity or higher. And 46% of those issues were able to be flagged directly to engineers writing their code rather than to security engineers. And that's an important number because that means we had those issues were high enough signal that they could be reported to engineers and we could be confident that they were going to be true positives. So beyond our knowledge from building Zonkalon for hack code, static analysis is just a great tool for automating security reviews and letting us scale up as a security team. So when I talk about scaling, one of the ways I'm talking about scaling is across the millions of lines of code we have at Facebook. If we do a manual analysis, either from a security engineer doing a security review or from an external researcher in the bug bounty program looking at a feature, they can identify vulnerabilities, individual vulnerabilities. With Pysa, we can take those vulnerabilities, encode that vulnerability class, and find it across our entire code base. When I talk about scaling, I'm also talking about scaling across the thousands of daily changes that happen at Facebook. Manual analysis, even if it's able to find every possible vulnerability in a given feature, can only discover issues at a point in time. With Pysa, we can keep checking for those issues into the future as every code change goes in. So does Pysa work at Facebook? I'd like to think that it does. It can give feedback to developers in 65 minutes. So when a developer proposes a code change, Pysa will analyze their code and will give them feedback and give them a chance to fix security issues before it lands. Additionally, 44% of the bugs that our security team finds in the Instagram server code base come from Pysa. As somebody outside of Facebook, you probably care more about how Pysa can work outside of Facebook. And we've tested it out, and it does work on projects outside of Facebook. we ran on a number of open source projects and privately disclosed remote code execution, server-side request forgery, cross-site scripting, and open redirect vulnerabilities, and even had one of the bugs recorded as a CVE. So now that you know a bit about why we built Pysa, why it exists, let's talk about how it works. Pysa works by performing static taint flow analysis. Static taint flow analysis is basically just tracking flows of tainted data from source to sink. When we talk about tainted data, this is basically any data that originates at or is somehow influenced by a source of data that we want to track. Taint sources are where we define tainted data to originate. Throughout the presentation, as I refer to taint sources in code, you're going to see this a lot, this annotation that says taint source and its name. Taint sinks are where we want to detect tainted data ending up. Throughout the code, throughout the presentation, when I refer to them in code, they'll look like this, taint sink and then a name for that sink. So a simple example of this, if we wanted to be able to detect remote code execution, our source would probably be user-controlled data. So for example, if you're writing a Django web server, one of the ways user-controlled data can enter your application is through the request.get dictionary, which contains all the parameters supplied as URL parameters. The sink would be any sort of code execution sink. So for example, one way to execute code in Python is through subprocess.run. So that might be the sink that we would define. So when using Pysa, there are two main inputs and then some outputs it's going to give you. So as an engineer using Pysa, you're going to give it models and rules. Models are PyI style stubs with annotations like the ones I just described that tell you what are sources and what are sinks. So in this example, subprocess.run, it was a sink we wanted to detect for remote code execution. So we would annotate the args parameter there as a taint sink for remote code execution. And by the way, if you're not familiar with what PyI style stubs are, it's fine. We'll talk about them later. For now, all you need to know is that they roughly look like Python code. Rules describe which sources and sinks we care about combining. So in this case, for our remote code execution detection, we want to know about user-controlled data flowing into remote code execution sinks. So when you give Pysa these two inputs, and of course your source code, Pysa is going to produce one main output, and that output is going to be issues. Issues are going to have lots of associated metadata with them, including traces, which are an important thing to help you debug and understand issues. So issues are basically just an indication of a potential vulnerability. They point to a specific point in your code where flows of data from a source meet a sink. Traces are just going to show you the call chain from sources to sink and can be really helpful when looking at flows of data that span many function calls. So going back to that CVE we talked about earlier, this was the source we used to detect that CVE. This is the request object, which determines or which indicates where user-controlled data enters the Zulip application. And this was the sink we used. This is Django's redirect function, and we labeled the location that's being redirected to as a sink. With those two models combined, running on Zulip code, we were able to find this CVE. So now we're going to go into the first exercise. The goal of this exercise is to make sure that everyone is up and running with a working environment and ready for exercise 1. So what you're going to need to do, you're going to need to clone this repository, github.com/facebook/pyre-check. Once you've cloned this repository, you're going to want to follow the instructions that are in that repository in the Pysa tutorial folder to set up your environment. Please note that we've only tested this on Ubuntu 18.04. That is both directly installed in your machine or installed under Windows Subsystem for Linux. And we've also tested it on macOS 10.14. If you're not on one of those operating systems, the best way to set this up is probably through Docker. So I'm going to give 5 minutes for everyone to get set up. Myself and some other tutorial facilitators are going to be available in Discord to support you with any questions you might have. All right, we're going to be carrying on now. For those who weren't able to get this set up in time, the tutorial facilitators will still be available in Discord to help you debug. And for those who are running Docker, you might need to give it a little bit more time to run. Hopefully it'll be done by the time we get to the next exercise. Let's start talking about the basic functionality of Pysa. For security applications, when I talk about tainted data, I just mean any data that needs to be treated carefully. So you can think of these as a bunch of different kinds of data. The biggest one is going to be user-controlled data. But there are other kinds of data that you want to treat carefully. For example, passwords need to be treated very carefully, or encryption keys need to be treated very carefully. Pysa is going to track the flow of this data from sources to sinks. So because security issues can be pretty severe, we tend to bias towards preventing false negatives. So this means that as data is transformed within the system, we need to make sure that taint persists even as that data is transformed. So let's take a look at this example. Taint is going to propagate through all these operations. So we start here with X coming from some source, some tainted source. If we add 10 to X, perform arithmetic on it, the result Y is going to be tainted. If we convert that result to a string, the result S is going to be tainted. If we convert that result, or if we run that result through a function where it goes in as an argument and comes out through a return value, the result I there is going to be tainted. If we take that value, put it into a format string, and assign that to F, F is going to be tainted. Sometimes, though, we can end up propagating taint too well. So if we say this entire object X is tainted, then if we put X into some sink, Pysa is going to detect that. If we put an attribute from X into a sink, Pysa will also detect that. If, however, we put a totally innocuous attribute, such as the double underbar doc attribute, which is basically it's the documentation string that would appear on a class or a function, that too is going to be detected. So sometimes we can get false positives like this, and this is something that we're going to come back to later. So recall that I said the two inputs that we need for Pysa are models and rules. Models are annotated stubs that correspond to your source code. So whatever you write in a model has to look pretty similar to what your source code looks like. Rules are the definitions for which sources we care about reaching which sinks, plus some additional data like a human readable name and a unique code to identify it. With Pysa, or in the open source pyre-check repository that Pysa comes in, we ship a bunch of pre-written models and rules. So we have models that cover all the basic standard library sinks that you might think of, like code execution and file system operations. And we also cover many sources for common web servers, such as Django or Tornado. When configuring Pysa, there's two important files to be aware of. The taint.config file is a big JSON document that has definitions for all the things we're going to talk about. So it has definitions for sources, for sinks, for rules, and for other things that will come up later. All the files with .pysa extensions are stub files. They contain models that tell Pysa what are sources, what are sinks, and a bunch of other pieces of configuration that you can give Pysa. All the sources and sinks that you use in your Pysa files have to first be defined in the taint.config file. So let's start with sources. Sources are defined in taint.config like this. They get their own JSON block, and each source consists of a name and a human readable comment to describe what it is. Once you put this in your taint.config file, you can start writing models that use it in your .pysa files. So models are going to apply annotations, those annotations that we talked about earlier, to that correspond to places in your code where sources appear. So in this case, if we're looking at cookies as a source, Django's HTTP request.getSignedCookie is going to return cookies. So in the place of a return annotation, we put taint source cookies. That's not the only place in Django where cookies can come from, though. Cookies can also come from HTTP request.cookies, which is a dictionary. So we're also going to label this attribute of this class as a taint source of cookies. So all the annotations that you see me applying in model files here and in other parts of the presentation are going to go in the exact same places that types are declared in Python 3. If you don't know much about Python 3 typing, that's fine. Throughout this tutorial, there's going to be lots of examples that you can copy that show you where to apply these annotations. But in the future, if you're ever wondering where you might be able to apply a Pysa annotation, it's a good bet that you can just look at the Python 3 typing typing pep and see where annotations are available there, and you can apply Pysa annotations in the same places. This is also a good point to stop and discuss these dot dot dots that you've been seeing. These dot dot dots aren't there to elide something because I'm lazy and don't want to type it out. The dot dot dots are literally meant to be present in your models. So Pysa model files are based on .py style stubs that we'll discuss later, and dot dot dots are there to elide content where the Python parser needs some content, but we don't really care to specify what it is. In this case, this is eliding the function body. It can also elide other things, such as you see down here, like the right side of an assignment. Sinks are very similar, or are defined very similarly to sources. They get a different block in the taint.config file, but otherwise they get a name and a comment just like sources. Similarly, they have models that are written in the Pysa files, and they have annotations. However, the annotations tend to go in different locations. For example, in our previous example, the source annotation was going on the return value of a function because the function returned tainted data. However, in this case, when we're executing SQL code, we're making the sink the command that's actually going to be executed. So we more often put taint sinks on parameters to a function and taint sources on the return values of functions. We can also taint an entire function to make all of that functions, taint an entire class to make all of that class's functions be sinks. So rules, you've seen these a couple times already. These go in the taint.config as well, taint.config file as well. They get their own section in the file, and they contain some of the data you've already seen, as well as some extra stuff that I've omitted so far, which is just a message format that allows you to make a human-readable output for Pysa. There's a few important behaviors of these .pysa files that you should be aware of. First off, you're allowed to define multiple models. For example, cookies are both cookies, but also they're user-controlled data. So you might want to define both of these models, and that's totally okay. Pysa is going to merge those internally. And additionally, Pysa is going to figure out some information on its own about what might be source and sinks in your program, and whatever it infers itself, it's going to merge with your explicitly defined models. Another thing that's important is that models need to use fully qualified names. So you can't just say class name dot attribute when you want to mark something as a taint source. You need to give the full import path. So django.http.request.classname.attribute. If this is in your own app, it might be my app, which is your app name, .module, .file, .class, .attribute. Model signatures need to match the code that they're meant to model. So the important places where they need to match are the function name, as well as the names of all the parameters. So in this example, we've matched the function name. We have the fully qualified name. However, as a typo, we typed out URI rather than URL. Having these parameters not match means that Pysa won't be able to realize that URL open corresponds to this URL open in code, and it's going to throw an error. So it's very important to make sure that the function name and the parameters match. So as I promised earlier, we need to talk about PyI stubs for a little bit. So Pysa uses pyre underneath to get a lot of information about Python source code. And Pysa models need to correspond to the source code that pyre sees. However, pyre is not always going to be looking at the original source code. Pyre sometimes looks at these .py stub files rather than the original source code. So these stub files are syntactically valid Python, and they provide information to pyre about the structure of the library and its types. Stub files were introduced because not all libraries have type information, and some libraries are too dynamic for a Python type checker to really understand what's going on. So stub files let us tell a little lie to the type checker to give it extra information that it needs to be able to run. For example, this is what the stub file for URL lib, or this is what a portion of the stub file for URL lib looks like. So syntactically valid Python, it uses those ellipses to elide function bodies, like I mentioned earlier. You'll also notice that it looks very similar to .pysa files. The only real difference between the .pysa files and the .py stub files is that the .pysa files use fully qualified names versus the .py files do not. So Pyre has two main sources for stubs. It uses Typeshed, which is a shared repository of stubs, and its own internal repository of stubs that are located in the stubs folder. Typeshed is a repository of PyI stubs that is shared by many Python type checkers. It covers the standard library as well as a number of common open source libraries. For anyone who wants to take a look at it, it's available on GitHub. So, as I mentioned already, Pysa models rely heavily on the PyI stub format. So if you're wondering about what might be possible in Pysa models, the PyI stub format is a good place to start. Now we're going to do a guided exercise. So the goal here is for you to follow along with me on your own computer, and we're going to explore the first exercise folder together. By the end of this, I'd like for you to understand configuration files, the configuration files that Pysa uses, and get Pysa to run successfully for the first time. So to start off, you're going to be navigating to the exercise 1 folder in the Pysa tutorial folder. All right, so in this folder, and in every folder, we have a README file. It's important to read the entire README file. I'm going to quickly walk you through some of the different files that are mentioned in this README file. So the first file that's mentioned is this views.py file. This file is meant to look like a Django views file. So for those who aren't familiar with Django, basically this function is meant to be an entry point to the program. So it's receiving a request object, which represents the request coming in from the user. When we call request.get, we're retrieving data provided by the user. So in this case, the user has provided an operator, and the goal of this function is to perform whatever arithmetic operation on 2 2s that the user requests. So obviously we have a remote code execution vulnerability in here because the user could put something other than an arithmetic operator in here. The goal for this exercise is going to be to detect this vulnerability. Going back to the README, the next file that we want to be looking at is our taint.config file. In our taint.config file, we've got all the sections we've talked about already. So we've got sources, which define our sources and provide a description for them. We've got sinks, which define our sinks and provide a description for them. We've got this features block, which we're going to discuss later in the presentation. And finally, we have a rule that connects these sources and sinks together. Now that we have these defined, we can go into the .pysa file. In the .pysa file, you can see here we've declared that request.get is a source of user-controlled data. Similarly, we've declared that this eval built-in function is a sink for code execution. So these two models are what we need for Pysa to be able to discover the flow that we were looking at in the .py file. The final piece here is the pyre configuration file. So Pysa piggybacks on pyre's configuration format, and so some Pysa configurations are in here as well. Looking at source directories, this is telling Pysa to look at code that's in this current directory. Taint models path is telling Pysa to discover the .pysa files and the taint.config files also in this directory. Search path is telling Pysa that it can find the stub files that it needs, or is telling Pyre it can find the stub files that it needs up 2 levels and in that /stubs folder that I mentioned in the presentation. This exclude isn't too important. It's just to reduce some noisy output that you might see otherwise. All right, so now that we know all that, we're going to go and we're actually going to run Pysa in this exercise folder for the first time. So all you need to run is pyre-analyze, and that kicks off Pysa. So there's a little bit of a startup cost. And the startup cost is increased a little bit because I'm running in a Docker container. And the end result here is that Pysa has discovered one issue, the one we wanted it to catch there, which was a remote code execution problem. You don't need to worry about this debugging output up here. It's not related to the exercise. All right, so now that we've walked through that together, it's time for you to try the second exercise on your own. The goal of this exercise is for you to gain a little bit of experience with sources, sinks, and rules. So if you're already in the exercise 1 folder, just go up 1 level and over to the exercise 2 folder and read the background information in the README. It's really important that you read the background information and don't just jump to the instructions, because there's information in that section that's going to help you complete the exercises much more easily. So once you've read that background information, you can jump to the instructions. So I'm going to pause for 10 minutes to let everyone work on the first exercise. Myself and the other facilitators will be available in Discord for support, and then we'll come back in 10 minutes. All right, we're going to carry on now. For anyone who's not finished, the tutorial facilitators will be available to help you out in Discord. So let's talk about how Pysa really works now. In order to do what Pysa does, it needs to compute summaries for all functions. Summaries describe which function arguments eventually hit a sink, which sources the function eventually returns. It's important to note that I'm saying eventually because I'm not just talking about the sources and sinks that are directly within the function we're looking at. It's also in all the functions that the function we're looking at calls. So if my function returns the result of another function which returns the source, the summary needs to capture that too. So in order to compute this, we do multiple rounds of iteration. We start off with an input of a model describing that this function source is a source type of user controlled. I've just abbreviated it here. Then Pysa starts looking over our code and reaches a function like this, which returns the value that source returns. And so at the end of this iteration, Pysa outputs a summary saying that the function here also returns a taint source of type user controlled. When we go to the next iteration, we take the summary as one of our inputs, and when we find another function, this wrapper function that returns source, then we compute another summary as an output saying that wrap source also returns user controlled data. Sinks work in much the same way. So if we have an input of a model that describes this argument as a taint sink for remote code execution. As Pysa iterates over our code, if it finds a function like this, where its argument eventually reaches this sink, then it infers a summary and says that calls sink is also a taint sink for remote code execution. Going into the next iteration, we take that summary as an input and continue iterating over the code until we find a function like this. And this wrapper function eventually calls sink. And so from there, we can infer that wrap sink is also a taint sink because its argument eventually reaches a taint sink of remote code execution. One of the things I left out when I was saying that this is how Pysa works is that our summaries need to do more than just figure out whether a function returns a source or hits a sink. We need to understand how arguments propagate from the input to the function to the return value in some way. So we call this TITO, or taint in, taint out functions. We don't need any models as explicit input to detect these functions. You can write models to help Pysa in cases where it can't figure it out on its own, but we're not going to talk about that in this presentation. So to start off, when Pysa is iterating through the code, if it finds a function like this TITO function, where argument ends up being returned, it infers a summary that says argument is a taint in, taint out argument, meaning any taint, so any source that goes into this argument is going to come out through the return value. In the next iteration, we take this summary as an input, and when Pysa sees somewhere else in the code that there's this function that wraps that TITO function, it can produce another summary that says wraps TITO is also taint in, taint out in that first argument there. This whole process is iterative, so we need to keep recomputing those summaries until we reach something called a global fix point. The global fix point means that none of the summaries are changing anymore. We don't want to look at every function again every single iteration, and so we can be a little bit more intelligent using the call graph to determine which functions need to be reanalyzed. So if one function summary changes in a previous iteration, then we know all the functions that called that function need to have their summaries recomputed in the next iteration. And finally, I left out one last piece about how Pysa works. Computing these summaries isn't quite enough. We need to be able to combine those summaries according to the rules that we discussed earlier into an issue. So recall, this is what rules look like. It's a description of which sources and which sinks we care about reaching each other. When a source reaches a sink, we're going to emit an issue. So carrying on our previous example with these summaries that we've inferred around wraps source, wraps TITO, and wraps sink, we can look at somewhere else in our code which might finally contain an issue. So we start off with the wrap source. Because it eventually returns a source, we know that X is tainted with source type of user controlled. Then when X passes through TITO, or wraps TITO, because we know that that function is taint in, taint out in the argument, we know that any taint that went in comes out the other side, and so we know that Y is tainted as well. And then finally, when Y gets passed into wraps sink, we have our source, user controlled, reaching a sink of type taint sink remote code execution. So this is the point where we're going to emit an issue. It's important to note that when Pysa emits issues, the line of code that's pointing to is this line right here, where we've combined, where the source flow and the sink flow have joined. So it's not necessarily the point where the source is or the point where the sink is. It's often somewhere in between. So when Pysa emits an issue, it's just going to emit a block of JSON output that tells you that this is an issue and give you the code and a bunch of other data about it. So this whole thing forms kind of an inverted V shape or a tree shape. Sources and sinks are going to be propagating up the sides, and they meet at the apex where we have our issue. We can have arbitrarily long call chains between the issue and the source and the sinks. It can get really, really long. And we can also have more than one source or more than one sink. So you can have two sources of user-controlled data that get combined and then passed into a sink, or you can have one or more sources of user-controlled data that end up in multiple sinks. Those taint in, taint out functions I described appear as a loop on this graph. So data is going to propagate down into one or perhaps a few lower level functions, but it always comes back up and then continues propagating. Those loops can appear anywhere on this. So let's talk about false positives now. Like any static analysis tool, Pysa can have false positives. I already alluded to that earlier when I gave this example. Because we treated this X object as tainted, any attribute that was accessed on this object was also treated as tainted, which meant that we might end up raising an issue for something like underbar doc, which is clearly not a problematic flow. So that was an example of a false positive. Other times, we have a truly valid flow of data, but there's something that's being done to that data to encode it or sanitize it or make it safe to use. So in this case, we have a simple example of reflecting user-controlled data into some HTML output. However, in between there, we're using the escape function, which will properly HTML encode that data and make it safe to put into HTML output. So while the flow of data is correct, user-controlled data does go into HTML, it's rendered benign, and so we wouldn't want to find this issue. So we'd count this as a kind of false positive too. Additionally, sometimes transformations render a source benign for some kinds of sinks. Not all sinks, but some kinds. So for example, let's look at this SQL injection here. If we have this user-controlled user ID here, and we put it into a SQL statement, if this was just any arbitrary string, that could potentially be very bad. However, converting it to an integer dramatically reduces the chances or options for exploiting an issue like this. So we might not want to be surfacing issues like this. Finally, we might validate data before using it. So in this example, looking at an open redirect, we have user-controlled data indicating the next URL, but then we make sure that it's a relative URL before actually doing the redirect. So in this case, we've asserted that it's valid data, and again, while the flow of user-controlled data into the redirect is truly a real data flow, it's not totally falsely identified. It's just not something that would necessarily be interesting or be considered a vulnerability. So Pysa offers two different kinds of tools for addressing all these false positives. We have sanitizers and features. Sanitizers are a more blunt tool. They're a mechanism to completely stop the propagation of tainted data during Pysa's analysis. Features offer a little more nuance. They're a mechanism to add metadata to the flow of tainted data, and then we can use that to filter out issues after the analysis is done. So we'll start off by looking at sanitizers. They break the flow of tainted data by removing any taint that passes through them. Sanitizers are written using models, just like sources and sinks were, and they're defined in .pysa files, just like sources and sinks were. So for example, this is what a function sanitizer looks like here. In the position of a return annotation, we add the word sanitize, and this tells Pysa to remove any taint that passes through the return value of this function. Note that that can be taint that enters through an argument and then is returned, or it can be taint that's accessed within this function and returned. In both cases, Pysa will remove the taint on that data and will not detect any flows that pass through the return value of this function. So going back to our previous example, if we wrote this sanitizer here and ran it on this code, we would no longer be detecting this as a cross-site scripting issue because we would stop the flow of tainted data here, and Pysa would have no idea that safe name was tainted as user-controlled data anymore. We can also mark attributes as sanitizers. So we just put the word sanitize in the same position where you put a type annotation on that attribute, and that'll stop any tainted data from propagating through that attribute now. So even if the whole object is marked as tainted, when we access that attribute, we'll remove any tainted data or any taint on that data, and we'll stop tracking the flow at that point. So in our initial example where we were concerned about this underbar, double underbar doc attribute being detected as a false positive, using this sanitizer would prevent this false positive from being detected. So sanitizers are really useful when you have explicit sanitization or encoding going on in your code. For example, the escape function that we talked about is specifically to prevent cross-site scripting by doing HTML encoding. So it's a good candidate for sanitization. Also, there's sometimes functions or attributes that always return safe data. For example, that double underbar doc attribute is always just a doc string. So it's not really going to be user controllable. Additionally, things like randomly seeded hash functions and stuff like that end up transforming data in such a way that's usually not going to be user controllable or not that interesting. The thing to be wary of, however, is that sanitizers are universal. That means they're going to return all taint regardless of what source was going in and what sink it was headed towards. There's no way to make them specific to a rule, specific to a source, specific to a sink. That means that when you add a sanitizer, you could remove false positives for one rule, but you might accidentally break another rule. For example, when we were talking about escape and making escape a sanitizer, what happens if we had another rule for detecting encryption keys on the server and making sure that we don't leak those encryption keys back to any external user? If we happen to run those encryption keys through the escape function to properly HTML encode them before rendering them into the page and returning to the user, we wouldn't detect that flow because escape function would sanitize the taint that marked that data as an encryption key. So now we're going to go into an exercise and practice using sanitizers. Our goal here is just for you to gain some experience and get comfortable using sanitizers. You're going to want to go to the exercise 3 folder. And again, just like the previous exercise, make sure you read all the background information before you go on to the instructions. I'm going to leave us 10 minutes to work on this exercise. Myself and the other tutorial facilitators will be available to help you out during this time. All right, we're going to carry on now. For anyone who hasn't finished the exercise, you can continue working, and the tutorial facilitators will be available in Discord to help you out. So now let's look at the second way that we have for fixing false positives. We're going to use features. Features are our term for additional metadata that we add during the analysis that can be used to filter out issues after the analysis is done. So these features are associated with an individual issue, and each issue is going to have a number of features attached to them. Some of them will be automatically added for you by Pysa, and in cases where the automatically added features aren't giving you enough data you need to be able to filter out the issues you want to filter out, we have a rich system for manually specifying more. So one of the simplest automatic features is the type feature. The type feature is just telling you that the flow of data passed through a conversion to the specified type. For example, type bool will tell you that the flow of data passed through a conversion to Boolean. Type scalar will tell you the flow of data passed through a conversion to any numeric type. So int, Boolean, floating point numbers, that kind of thing. So if we go back to that SQL injection example we had earlier, where the user-controlled data was converted to an int, now we have the type feature, which we could use to filter out issues like this, which are going to be less interesting to us. One of the other things we have is a prefix on other features. So this always prefix is going to be automatically added to any feature that is present on on every single branch of a flow. So remember how I talked about multiple sources could potentially be involved in an issue and multiple sinks could be involved in an issue? So if every single branch leading from a source to your issue or from a sink to your issue has a feature on it, then that feature will be given the always prefix. So for example, if we're doing this simple remote code execution operation here, or something that looks like remote code execution, we have both a left value and a right value, which are both user-controlled data. So we have two sources going into one sink here. Both flows, in this case, pass through conversion to Boolean. And so we'd end up with a feature that says always type Boolean because every branch passed through that conversion. If, however, the left value here wasn't converted to Boolean and the right value was, we would have one branch which wasn't converted to Boolean. And so we couldn't add the always prefix and we would just get the regular type bool feature. It's important to note that the always prefixed version of a feature is going to be exclusive with the non-always. So you should either see always type bool or type bool and not both. So another kind of automatic feature that we add is a via feature. Via features tell you that the flow of data passed through some kind of special or interesting function. So the first kind of via feature is called via obscure. Obscure functions are functions where Pysa doesn't have the source code to analyze. And so we're going to assume by default that the functions are taint and taint out. Any taint that goes into the arguments comes out the return value. When we do make that assumption, we also add that via obscure feature. This helps you be aware that you might have some false positives on this flow because of this assumption that we've made. Another via feature we offer is the via format string feature. This feature means that a flow passed through a Python f string. For those who aren't familiar with Python f strings, they're a special kind of formatting string where you prefix with the f and then write a normal string, and you can reference local variables inside the string with these curly braces, and they'll be inserted into the string. They'll be converted to a string and then they'll be inserted wherever you place the curly braces. Because this isn't passing through a function, you can't manually add some sort of feature. So we automatically add this feature in case you are interested in flows that pass through these kinds of string formatting. The final automatic via that we add is via TITO. So this tells you that the taint passed through a taint and taint out function. Those functions, if you recall from our earlier example, are functions where data goes in through the argument and comes out through the return type. So via features can also be added manually, and they're one of the features that you most often want to add manually. Those manual via features indicate that data passed through whatever point in code that you annotate. So for example, I might want to add a via get attribute feature, which would annotate the get attribute function and say that data went through it. When you're declaring your own features, just like sources and sinks, you need to first declare them in your taint.config file in their own block. So here we have an example of me declaring that getAttribute feature I referenced, or any other feature you want. These names can be whatever you want, and the comments describe what they are. Then, when you're using those features that you declared in your .pysa files, you're going to be writing with the same model syntax that you wrote sources and sinks with. You can add features in virtually any place. So, for example, you can add a feature to a flow right at the source where it's declared. So, before we would declare a taint source of user controlled data and just close it here. But instead, we can add a comma and also say via request files. So this is adding a feature to any flow that comes out of this files object. Or I mentioned earlier that you can explicitly declare taint in taint out functions. If you explicitly declared a taint in taint out function, you can also put the via declaration in there and tell it via getAttribute. And then any data that has gone in through this O value and come out through the return value of getAttribute will have this feature attached. Sometimes you don't want to be adding a feature right at the place where you've already got a source declaration or a sink declaration or a taint in, taint out declaration. There's lots of other ways that you can add features, but the only other one we're going to cover in this presentation is add feature to argument. So this functionality lets you attach features to any data that touches a point in code, regardless of whether it comes from a source, a sink, anything like that. So for example, if we have this model, tainting something in my module called assert relative redirect, we can type add feature to argument via, and then specify the name of the feature we want to add. And that means any data that touches this URL, even if it doesn't go into the function and come back out, any data that touches this URL is now going to have this relative URL feature attached to it. Now, using that model we just wrote, we have a way to filter out the false positives from our earlier example. So if you recall that example, we took user controlled data, we asserted that it was a relative URL, and then we returned it to the user. Now, when we do this assert with this model from the previous slide, Pysa is going to detect this flow, but it's going to add that relative URL feature that we wrote a model for in the previous slide. So now we'll be able to filter out this issue after the fact, knowing that we have this, or based upon this via relative URL feature that we've added. So this was really just the tip of the iceberg. Features are an incredibly powerful and flexible technique for removing false positives. So if you get into using Pysa, go reference the Pysa features documentation, and you can see plenty of other ways you can use features and plenty of other ways you can add features. So to browse features, we're going to need to use a tool we haven't touched yet, the static analysis post-processor. So this tool lets you explore any of the issues that Pysa outputs and filter them in a number of ways. So it's going to show you additional metadata that the default output doesn't show you, such as features that we've talked about here and other things like trace links. It lets you browse the traces and follow them all the way from the source to the sink. And it lets you filter these down by common things you might care about, like filtering down to only look at issues for a certain rule, or only look at issues that have or do not have certain features, and many other options. Filtering with SAP is really the practical way to use Pysa. So we've been able to use Pysa and just look at the raw output for some of these toy examples, but when running Pysa on large projects, filtering with SAP is the way that you're going to want to browse your results. So when we want to use SAP, we have to slightly modify our pyre-analyze command to tell it to dump the raw JSON output to the local directory. We then have SAP analyze this JSON file and kind of export it for its own uses. And then we can go into explore mode, and we can launch an interactive session with SAP to look at the issues that Pysa has discovered. When we're in explore mode, the first thing we want to do is just see what issues there are. So this can dump a full list of all issues that Pysa has found. And already you can see that there's some additional metadata here that wasn't visible in the default output of pyre-analyze. So you can see that we include what features are present on the flow. And in fact, I ran this on one of the exercises that we already completed, exercise 1, and you'll notice that we were actually having these automatic features appearing even in exercise 1. Other data includes trace length and where exactly in your code the issue is occurring. So once we have an issue that we find interesting and we want to look into, we can type issue and then the issue number, and that'll focus SAP on that one issue. We can ask it to show us the trace from source to sink. We can look into any one of these trace frames, And from there, we can list the code and get Pysa to point us, or get SAP to point us to exactly where the source was or exactly where the taint propagated at any point along the flow from source to sink. When we want to filter issues, we can use some of the parameters that are available for invoking this issues command. So for discovering this kind of stuff, the help command is very useful. So if we run help issues, this will show us all the different parameters and what they're useful for. So the ones that are interesting to us are probably the codes parameter, which lets us filter down to different codes corresponding to a rule. So that code is that numeric value in the definition of the rule you've seen crop up a few times. And then here are some examples of the ways you can filter on features. So we can filter issues down to ones that contain an entire list of features, or that contain any feature from a list, or we can exclude issues that have a given feature. So some example queries, you could run issues and tell it to show all issues that have the always type Boolean feature. Or you could tell it you only want to see issues that come from rules with codes 1, 2, and 5. Or you could tell it that you only want to look at issues that have short trace lengths. So you want the easier to debug issues first. All right, so now that we know a little bit about using features and using SAP to browse features and filter based on them, we're gonna go into a practical exercise. So the end result of this exercise, hopefully, is that you're comfortable attaching features and looking at them in SAP and filtering out issues based on those features. So you're gonna wanna navigate to the exercise 4 folder. Just like previous exercises, make sure you read the background information before you jump into the instructions. I'm gonna give us 10 minutes now to work through this exercise. As with previous exercises, myself and the other facilitators will be available in Discord to help you debug and get unstuck. All right, we're going to carry on with the presentation now. The facilitators will be available in Discord to help out anyone who's still working through the exercises. So some sources and sinks might be too numerous or rapidly changing for a single user of Pysa to really keep up. Imagine, for example, you have a web application with thousands of different entry points of data. All those entry points could be changing constantly every day as developers write new ones or change existing ones. And even just writing models for those entry points initially would be a huge amount of work. Or imagine you have a database ORM with thousands of different classes representing different objects in your database, and all those classes have places where you can be storing data into that database. In both these examples, trying to write models and keep them in sync with the code is going to be a huge undertaking and result in a lot of effort and pain for the user. So our solution to this problem is model generators. Model generators are a tool that will analyze your code before Pysa starts to do its analysis, and they're going to output a list of Pysa models that Pysa can then use while it's doing its analysis. Out of the box, Pysa provides a bunch of pre-built model generators. These generators come in two flavors. General purpose model generators, which give you the building blocks to generate models for kind of any type of code you want, and then framework specific model generators, which use those building blocks to generate models for specific frameworks. So the general purpose generators include things like modeling all functions that have a given decorator, or modeling all constructors for functions that are descendants from some sort of class. Framework-specific generators include generators for all view functions in a Django web server, or all resolvers in a Graphene GraphQL system. So let's work through an example with Graphene. With Graphene, you have resolve functions, which basically allow you to look up data relative to an object. For those who aren't familiar in GraphQL, you don't need to know much about GraphQL, but basically when using GraphQL, you could query a user object, and then within that object, you could query their feed or perhaps their friends. So Graphene will dynamically look up functions based on those queries. So if you query feed on a user, it'll look for resolve underscore feed, and then it'll pass the data that you provide into the quargs argument here. Similarly, if you query friends on a given user object, it'll look for resolve underscore friends and pass the data you provide into the quargs argument here. Imagine we have a system with hundreds of these objects and dozens of these resolve functions on any of those objects. Obviously, that's going to be way too much to write models for manually. So here, you can see us putting the Graphene model generator to use to taint all of those resolve underscore functions. So we start some imports. We create a pyre connection. I'm hand waving this away. Basically, what it's doing is it's creating a connection to the pyre server, which allows us to grab some type information. We then set up the generator, give it a name, and pass in that pyre connection. From there, we call run generators. This does some helpful stuff like set up the command line interface and stuff for you. You can then select which modes you want to run based on the name you specified here, and the default modes will cause this generator to be run by default when you don't specify which modes you want to run in. It's that simple to start generating potentially thousands of models for a Graphene system. The output is going to look just like all the models that we've been writing throughout the course of this presentation. It'll figure out the fully qualified name for those resolve functions. It'll taint the arguments of those resolve functions. And by default, it's also going to taint the return value of those resolve functions, indicating that whatever data comes out of those is returned back to the user. Now we're going to go through an exercise putting those model generators to use. So our goal for this exercise is for you to learn a little bit about the model generators that are currently available to you and gain experience running two specific model generators. To do this exercise, you're going to go to the exercise 5 folder. As with the previous exercises, make sure you read the background information before you go into the instructions. And then once you've read that background information, go into the instructions. I'm going to give us 10 minutes to work through this exercise. Myself and the other facilitators will be available in Discord to offer you help. We're going to move on now, but the tutorial facilitators will be available in Discord if you're still working on the exercise and need some help. Now we're going to get into limitations. Just like every static analyzer, Pysa has limitations, and we've had to make some trade-offs when building it. The first limitation is around accuracy. Runtime and memory constraints force us to sacrifice some amount of accuracy to be able to terminate the analysis in a reasonable amount of time. One example of this is we limit the number of leaf nodes that we track when tracking taint. So if we look at this example here, we have a dictionary here with 20,000 entries, and half those entries contain user-controlled data, and the other half are totally benign. Pysa isn't going to be able to track all these entries separately, so we just collapse down the taint and say that the whole dictionary is going to contain user-controlled data. This means we might introduce some false positives when accessing a benign attribute like this one. Another limitation is caused by the dynamism of Python as a language. So Python has tons of flexibility, which is useful as a developer, but makes it hard for a static analyzer to detect some flows of data. For example, if we dynamically import and use a dangerous module, Pysa isn't going to be able to detect this. So if we take a look here, we can see that we're using import module to dynamically import the OS module, and we're passing user-controlled data into the system command, which executes code. Now, of course, you could say that we could parse this string and figure out what module OS was. However, we can come up with more and more contrived and pathological examples, such as making OS be externally controlled, and so there'd be no way to figure out what module is going to be imported until runtime. This kind of limitation usually results in false negatives because it means we don't know what functions are being called. Another limitation comes from typing. Python does not require static types, although it now has a type system that allows you to specify static types. We need types for Pysa to be able to figure out how to dispatch calls. So for example, if we have both bird and airplane, which implement a fly method, when we accept an object and try and call fly, without types, we don't know which method is going to be called here. So this, without having types, we can get both false positives and false negatives. False positives can come up from having obscure functions, so assuming that data that flows into a function flows out of the function through the return value, even though it doesn't. Or they can cause missed flows by not knowing when data flows into fly or any other operation, how it's being used after the fact. Additionally, it's important to acknowledge that although Pysa is a security-focused static analyzer, it can't detect all kinds of security issues. For example, let's say that our system is designed such that we have sensitive operations like delete user that are always supposed to be protected by a check to assert that the current user is admin. If our system was designed this way, Pysa wouldn't be able to assert that this check was performed because there's no flow of data that's passing through this user is admin here. We could detect request.get, we could detect this user-controlled data flowing into the delete user operation, but we wouldn't know that user is admin was checked before. Obviously, we could change this code around to create a flow of data that we could detect, or we could even change the code to make it more safe, perhaps by baking user is admin into delete user. But this example just serves to show that there are certain formulations of problems that Pysa is not intended and not capable of solving or identifying. So, in conclusion, Pysa is an open source tool that finds issues in Python code using a technique called static taint flow analysis. Taint flow analysis can be a really effective tool for finding bugs that can be modeled as flows of data from a source to a sink. Like all static analysis tools, Pysa has false positives, and we offer two different methods for dealing with them, features and sanitizers. When getting into larger Python codebases, model generators offer you a way to dynamically create models in order to save the work of writing and maintaining models. And of course, Pysa has limitations. Those limitations are based on the constraints we needed to make it run fast, and also based on the Python language itself. So now that you've made through this presentation, I hope you understand a little bit of how to use Pysa. My hope would be that you will go out and try Pysa on your own project now. If you do this, there's help that's available through the documentation at pyre-check.org. And also, if there's information that if there's something that's not available in the documentation or you think you find an issue, help is available through GitHub issues on the pyre-check repository. And finally, you can always reach out to me directly on Twitter at Bleaney. Thank you for attending this presentation. Thank you to the tutorial facilitators, Apoorv, Ibrahim, and Sinan, who've been helping you out along the way. And thank you to everyone else in this list who's contributed in one way or another to get this presentation out.